Hello, when we talk about relativity we always think of Einstein. It was not Einstein who discovered relativity, but Galileo. In 1905, Einstein took up Galileo's relativity to explain that in an inertial motion, such as that of the rigid rod that he measured, in the first chapter of his article, that this motion is like nothing and therefore that it does not modify the lengths in the direction of motion. Yes, it's off to a very strong start and I'm going to share my arguments with you. The first victim of the relativity of motion was Aristotle, who demonstrated the immobility of the earth on the grounds that an object falling from the edge of a table falls at its feet, whereas if the earth moved, it would fall further. It was Giordano Bruno, about 1850 years later, who first noticed that an object falling from the top of the mast of a boat in motion in a good breeze fell at the foot of the mast and not at the back of the boat. This and other ideas too modern for the time led the Catholic Church to condemn him to the stake. Galileo explained that the objects in the captain's cabin do not tell if the ship is stationary or moving. You have to look at the coast. Water always drips vertically. An object that falls off a table always falls to the foot of the table. And flies fly without having to struggle to keep up with the speed of the boat.
No matter how fast the boat is.
We can transpose to the cabin of an airplane in flight. The hostess fills your glass without any problem and without spilling liquid on your feet. You can go to the toilet normally on the way there and back. No way to know that you are moving at 560 miles per hour except to look out the windows. In the captain's cabin, there is nothing to tell if one is moving or not, the same in the cabin of an airplane, and Einstein extends this property to its moving rod. An observer who accompanies her is motionless with her and does not detect any deformation. The same goes for the traveling twin. Nothing deforms in his cabin, but he observes the deformed earth. The measurements are distorted because they are out of sync, says Albert. We have finished with this introduction, which is a bit long but necessary as the relativity of motion is poorly understood. And you will note in passing that it has nothing to do with the relativity of life used in literature and philosophy, which teaches us to relativize our problems and the great events that affect us so as not to attach to them an importance other than the one they have and to deal with them. I refer you to the specialists for more details. In 1905, in his article on the electrodynamics of moving bodies, Albert Einstein used the principle of the relativity of inertial motion to explain that the observed contraction of the rigid rod measured in motion in paragraph 2 of his chapter 1 results from the desynchronization of the measurements and not from reality. In a frame of reference in relative motion, the speed of this motion is undetectable because no change can be observed. The stem remains the same length. As far as the desynchronization of the measurements is concerned, it is the fact that the light from the frame of reference of the moving rod travels with the rod at the speed c, and the motionless observer by convention measures the rod with his own light also at the speed c that runs after the point b that moves away at the speed v relative to it and then back with a point a that gets closer. Einstein measures the outward time, Tb minus Ta equals Ab divided by slash, c minus v, and on the return time Ta minus Tb equals Ab divided by c plus v. The change of frame of reference induces an apparent contraction which is observed but does not correspond to the reality of the relative inertial motion. It is also relativity that explains why the high-speed traveler in a spacecraft is seen contracted in the direction of motion from the Earth while he notices nothing, believes himself to be motionless, and observes that it is the Earth that is moving away and is contracted in the direction of its motion. Langevin had not spoken of the speed but of the very strong accelerations for his traveler, which had slowed down the passage of its time in relation to that of the Earth. Einstein, when asked about the question of twins, replied the change of frame of reference. Translate as the accelerations at the start, braking and U-turn, reacceleration and final braking of the traveling twins. Not the speed, which is relative. Above are excerpts from the second paragraph of the first chapter of the 1905 article, where Einstein explains that the measured contractions result from the desynchronization of the measurements. According to the principle of relativity, the length found by operation A is equal to the length of the rod in the stationary system.
University of Oxford Department of Physics.
That will be all for today. It is already a lot. Next time we will see a hypothesis that is both simple and astounding, which confirms Einstein's second postulate. The one that says that the speed of light is the same in all reference frames. You will say that it didn't need to be confirmed. I wouldn't discuss it. But it's a powerful argument to test my hypothesis, which obviously needs to be confirmed, all the more so since it is apparently irreconcilable with relativity. The expression, which is only apparently irreconcilable, is used by Einstein himself to say that his second postulate, which is only apparently irreconcilable, wish the former. There is a sequel. We had to start by demystifying Einstein's special relativity, which is in reality the principle of relativity of Galileo's inertial motion, and which explains that the speed of such a motion is undetectable locally, and that it does not modify in any way either the lengths or the dilation of the flow of time. Einstein explains that Lorentz was mistaken, but in removing the ether, a fatal mistake at that time.
Lorentz was preferred.
Minkowski, Einstein's maths teacher at the Zurich Polytechnic whose classes Einstein skipped, took up Henri Poincaré's 1906 publication, presenting the Lorentz transformations, with Poincaré's very high-level mathematical developments, but without taking into account the relativity of motion. Its spacetime is brilliant, but the lengths of moving objects are contracted, which contradicts Galileo's relativity.